Good afternoon. Thank you for coming to our session. I hope you've been having a great day here at re:Invent. Obviously, you might be having a little bit of difficulty with my accent, so if you want to come and watch it on YouTube after a few reruns of Braveheart, that's probably fine. As you know, there's no QA session. I will be outside later on for QA. I'd also point you either the security booth, the CloudFront edge services, or ask an expert down in the main exhibition hall. My name's Andrew Kiggins. I'm a development manager in Edge Services, and my team's focus on anti-DDoS technology. I'm joined today by Adrian Newby, CTO of CrownPeak, a long-time AWS Technology Partner. Availability is one of AWS's top priorities. DDoS has the potential to impact that availability. And if you've got no defense in place, even a small DDoS can have a significant impact on that availability. So today, we're going to look at some techniques and resources that are available in AWS and with other technologies that you can employ to build a DDoS resilient service. We'll briefly look at the landscape this year, in the last 12 months, what we've seen in the DDoS area. Then we're going to look at specific techniques and ways that you can build a resilient service. We'll look at some reference architectures against specific DDoS attacks. And then I'm going to hand over to Adrian, who's going to walk us through a real-life attack where CrownPeak defended a customer based in AWS. So, where are we from last year? DDoS falls into two broad categories: infrastructure and application layer attacks. Infrastructure attacks target layer 3 and layer 4, your network and transportation layers. They're not trying to take down your servers. They're not trying to destroy your firewalls. What they're trying to do is make it impossible to serve traffic. Infrastructures level attacks, you may have heard of in the press, 100 gigabits, 200 gigabits, 400 gigabits. That's not the norm. In fact, it's highly unlikely you'll see any kind of attack. The average attack size is just under 1 gigabit. Half the attacks are 500 megabits or less. That's actually quite manageable. It is, however, the predominant attack type, just under 80%. Why is that? They're really easy to launch. Anybody with a credit card, in many cases their parents' credit card, can launch a DDoS attack. Just go out, pull out your credit card, rent a botnet by the hour. This is your third, maybe your fourth day in Las Vegas. By now, you should be very suspicious of things that you rent by the hour. Of course, the other type of attack, application layer attacks, make up the remaining 20% or so. Predominantly, these attacks target Port 80, 443, HTTP web servers. It doesn't mean you don't get them in SNTP servers, NNTP, FTP. They're all valid applications. They've got internet ports that are open. But they're more complex attacks. They're harder to launch. So your script kiddies typically don't do that. It typically needs a little bit of information about the application. They've identified resources, weak links that are vulnerable to DDoS. Another thing we've been seeing is multi-vector attacks, where multiple attack vectors are being launched simultaneously. You have a SYN flood against your application. You've got a reflection against your DNS infrastructure. They're harder to launch. They're also harder to defend. It's harder to get the analytics of what exactly is going on. and you've got to put in multiple mitigations to defend it. Amplifications, very popular last year, still very popular. NTP, and these are in order of size, still a very large player, but again, we're starting to see SSDP as flavor of the month, something that's popped up quite recently and is being used extensively. There's also some new attack types coming along. I call these hit-and-run attacks. They appear, fairly high volume, and then they disappear. You think you're done, and they appear again, and then they go away, and you're never quite sure whether the attack's over. And they're going after the human factor. If these things are lasting for 2 and 3 days, that's significant stress on the operators. Maybe there's handoffs in there, shift changes, there can be loss of context. As operators get tired, they start to make mistakes. The other thing we've been seeing is DDoS used as a smokescreen. Everybody's really worried about this massive DDoS attack that we're experiencing, and they don't notice the password cracking or the cross-site scripting attack going on underneath. Let's very quickly run through what these attacks look like. Infrastructure attacks are going after your protocols, your routers, your firewalls, your transit links. The SYN flood attack is taking advantage of a nuance of the TCP protocol. A standard TCP connection has a source and a destination. You initiate it with sending a SYN. The recipient responds with a SYN ACK. And the nuance here is that when that happens, it takes a small amount of memory in the connection table. The connections get completed, and in due course, the connection gets torn down. All's good. In a SYN flood attack, the SYN comes, the SYN ACK's responded to, the memory is allocated in the connection table, but the connection is never completed. So, as the attack continues, you slowly fill up the connection table, and eventually, the valid requests can't be honored. UDP floods, and in this case, we're going to look at an amplification attack, a common mechanism, like using an NTP server. Similarly, you have an attacker and a victim. And there's a third part here. You have an amplification device, a reflector. In this case, it's an NTP server. NTP is a feature that allows you to request a large amount of data called monlist. You send a small packet, 64 bytes, and you get a 2,500 byte packet back. That means when the attacker spoofs the victim's source IP, that response packet is going back to the victim, not to the attacker. So by using that amplification mechanism and a botnet, you can generate a very large amount of traffic towards the victim. And DNS, SNMP, SSDP have similar amplification vulnerabilities. At the application layer, flood-style attacks are still common. And the difficulty here is that often they're well-crafted. It's difficult to differentiate between the DDoS traffic and the regular traffic. And when those floods come in, then your server becomes overwhelmed. You can't handle the number of connections, and the valid users can't be served. One way of exploiting the HTTP protocol is by using slow LoRa's. Now, if you do a wiki search, what you find is this really cute little mammal, big eyes, and it looks fairly innocuous. It also has really big sharp teeth, and it's highly toxic. Apparently it's got toxic elbows or something. And that's kind of what this is. It's this very small attack, and it plays out its characters bit by bit, and it exploits the fact that HTTP will allow you to hold that connection open, so as it gets played out over a long period of time, valid users can't get a connection. So what do? How are we going to mitigate this? Well, the first thing you have to think about is you don't know the volume. It could be a 15 megabyte attack. It could be a 10 gigabyte attack. You may not know the vectors, and you may not know the target. So having a flexible response with defense in depth that you can scale up in response to the attack is vitally important. And we're going to look at some techniques that allow us to do this. You want to minimize the surface area. Give them less to hit. You want to know your traffic. One customer's traffic is very different from another's customer's traffic. And if you can figure out what your traffic looks like under normal circumstances, you can figure out what it looks like under an attack, and then you can get rid of the bad traffic if you know what the good stuff looks like. You want to be able to scale. Scaling buys you a lot of things. It means you can absorb very quick spikes, and you put the onus on the attacker to respond. Some resources can't be scaled. Maybe it's an expensive resource. Maybe it's a database, monolithic database. So you've got to pay particular attention to those weak links. Also, trying to plan when you're under attack is very, very hard. So planning in advance is very, very important. So let's look at these individual things. Minimizing your surface area. If there's servers that don't need a public interface, don't make them public. Hide them in the back where they're not reachable. If there's resources that you're really not bothered about during the DDoS attack, maybe it's a system that only gets used once a month, don't expend resources on it. It's more for your operators to monitor and watch out for. For the things you do need to expose, make them difficult to find. If you've got multiple applications, spread them out on different IP addresses, because then if an attacker can find your FTP server, it won't have the same address as your web server, so he can't make that connection. Amazon VPC has features that lend themselves very well to this. Here we've got a web application server with a MySQL database backend. The first thing I want to do is put them in a private subnet inside my VPC. That means externally they're not visible. The IP addresses that those have are not reachable. The next thing I want to do is segment my ingress points. And here we've separated out the administration plane, the user plane, and my external access. The user traffic comes in through the ELB and hits the web server. And here you'll notice that in the ELB, we've changed the port. So while your typical web traffic's coming in on 80, this web traffic's actually being served out of 80. So even if someone does get into my VPC somehow, the port's not where they're going to expect it to be. My admin traffic, I'm putting through a separate server. And my outbound traffic is handled by the NAT device. Why is that important? What this lets me do is set up different security groups according to the needs of those connections. So I can constrain what type of user, what subnets, what geolocations can actually get into my application. Route 53 and CloudFront give us some other advantages. Under normal circumstances, I use Route 53 to discover my CloudFront distribution. If CloudFront hasn't cached it, I send it to my origin, and I get my content. In Route 53, if I set up an alias with a CNAME instead of an IP address, when the attacker tries to discover where the traffic's going, he's only going to get as far as CloudFront. And as we talk about later, CloudFront's really good at heavy lifting and something that's you can really take advantage of in a DDoS scenario. The next thing is understanding normal behavior. And this is around levels, the traffic patterns, the diurnal waves that you see in your application. It also means understanding where your spikes are. When do you get your resource spike? Do you have a lot of flash crowds? Do you have a very steady level of traffic? Knowing what they are and when they come allows you to respond. You can spot the abnormalities, and further, if you know what the normal levels are, you can alarm when they become abnormal. If you do experience a DDoS attack, you have the data should you need to engage with law enforcement. You can review that data to improve your resiliency. CloudWatch monitors a large number of metrics. By understanding your data, you can set alarms that are going to advise you when things go out of range. Now, hold this thought, because this is one of the points that Adrian's going to address, and it's very important. The next thing is scalability. Scalability is great. You can scale up when the attack comes so that you don't need those resources spun up all the time. If they're correctly deployed across multiple areas, multiple regions, as well as making your DDoS resilience very strong, it gives you a lot of resiliences in face of disaster, be it software failures, hardware failures. So there's a side benefit there. It makes the attacker work harder. Attackers are generally lazy. They're going to go after the low-hanging fruit. If you make it harder for the attacker, they're going to be less incented to come after you and attack. It gives you flexibility both at the instance level, where you can scale your capacity, and at the network level, that you can take advantage of really large pipes and multiple pipes coming into your application. Moreover, if you scale automatically when the attack comes, it gives you a little bit of breathing room to dig in and look and see what's happening in the attack, to see if you need to take other measures. Now, there is an elephant in the room. You may or may not have spotted it here. What does this cost? I'm going to defer that to Adrian, who'll give you very real numbers of what it costs to defend a DDoS attack in the Amazon infrastructure. So how do we scale? So here we see the user coming in, comes through Route 53, hits the ELB and goes to the web server. Life is good. When the DDoS attack comes, we may have to scale up our back-end instances. We can choose larger instances, or we can spread them out using lots of smaller instances. What works for your application, you have to decide for yourselves. Both are applicable. It's a very application-specific thing. We can also scale up. ELB is going to take off that load for us as well. But really, we want to push that scrubbing out as far as possible. And by using CloudFront Route 53, we can take a lot of that off. I'm going to cover exactly what CloudFront will do for us. But suffice to say, a lot of this traffic, the DDoS traffic, bounces off. In scaling, Amazon has 11 regions. Those regions have really fat pipes out to the internet. That just comes with the architecture. If one of those pipes is down, we still have resiliency. We've got 2 other ways in. We guarantee availability. If 11 is not enough, we leverage edge services, 52 edge locations, similar, multiple transits, multiple resiliency. CloudFront also has some other nice features. We're serving your HTTP traffic, but that's all we're going to serve. HTTP traffic runs over TCP, so any of these UDP amplification attacks, they're simply taken off the table. By moving out to CloudFront, you make CloudFront do the heavy lifting. Invalid object requests, Hulk attacks, malformed requests, they're just not going to be served, and they're never going to hit the origin. With the geo-restriction feature, if you're mostly serving out of North America, for example, you can restrict the regions that traffic's accepted from. Route 53 has resiliency built in with anycasting and shuffle sharding. Anycasting means your request is going to be served from the nearest location. If that location's down, you're automatically going to be served out the next nearest location. With shuffle sharding, it means, skipped on a bit, sorry about that. Shuffle sharding means that any hosted zones are not going to serve by the same set of servers. That means any impact on one hosted zone is not going to impact the next one. There's going to be points in your application that may be weak. They may only handle a certain number of requests per second. You want to put additional measures in place to protect those, such as rate limiting, controlling the access. If we put the correct ACLs and security groups in, that gives us some coverage, but we can complement that by putting specific rate limits and access controls for those servers, for those applications. And it's going to make sure that our legitimate users are prioritized and get availability. One way of doing this is by using a web application firewall. Now, a web application firewall is predominantly a security device. So one of the foremost things that you want is the OWASP top 10, your vulnerability scanners, your ability to eliminate cross-site scripting. So that's kind of table stakes. Other things you want are the ability to rate limit, blacklist. Some applications, you know who the good actors are, you know who the bad actors are. Take that off the table by blacklisting them and whitelisting them. We talked about auto-scaling. You don't want to put in a choke point. So by having native auto-scaling in your WAF application, it allows you to scale with your ELBs and your auto-scaling instances. Finally, a learning engine built into the WAF. If you know what the good traffic is, and many WAFs have the ability to learn that traffic, what page sequences are being hit, what URLs are common, which parameters are used for specific pages, they can then filter out the requests that aren't good. These things can all be deployed in EC2, and they're available for the Amazon Marketplace. We've got 15 different options out there. You have to evaluate the one that works for your application. There's a number of different payment models. Bring your license, pay as you go. Again, very application specific. This is how we deploy the WAF. Best practices, and in this scenario, WAF could be an HA proxy, it could be a caching engine, and they all work in the same models. You have front-end load balancers to spread the load across the WAF, and then an ELB to spread it across your web services. You want to separate the management and the application traffic so that as those WAFs or HA proxies scale up, the configuration plane automatically downloads the correct configuration. Number of other mechanisms that you can employ: HA proxies, varnish. If you've got Apache, you can use mod security. There's a number of good sessions on the web track. I was just at one earlier on, 204. There's a 301 session where they go into these in more detail and talk about varnish and Nginx. Highly recommend you getting those on the YouTube. Unfortunately, they were earlier on, so if you missed them, you have to catch them on YouTube. I want to very quickly now talk about how these mechanisms can be used to respond to individual DDoS attacks. And UDP Flood is a very common one. As your user comes in, he's hitting your web traffic, your web server. When you get a DDoS hitting the web server, the first thing you want to do is make sure you've got a security group inside your VPC. That allows you to restrict the traffic. With an ELB in front, we can push that traffic further out. ELB doesn't support UDP, so the ELB is simply going to discard any UDP traffic. Pushing it out further to CloudFront allows you to take advantage of the CDN by taking that large geodispersion taking available of the very diffuse nature of how we can take these very large attacks and spread them over a large number of edge locations and drop that traffic. SYN flood, a little bit different. The user traffic hits the web server, and when the DDoS traffic comes in, again, we put in a security group with the restrictions, maybe by geolocation, maybe we know the source IPs, maybe we know who the good actors are again. We put an ELB in front of it. Now, this is slightly different because the ELB in this case is going to terminate those SYN connections. Obviously, the ones that are not valid won't complete, and they're never going to get passed on to the back end. If CloudFront's in front of it, again, those SYN floods are simply going to be discarded. HTTP floods, the application layer. When the DDoS comes, the first thing we want to do is use our auto-scaling to absorb. Put a security group around, simple best practices. But then we want to employ the sandwich with the ELB at the front, the WAF or the HA proxy, maybe a caching layer based on varnish, and an ELB in the back end. Again, by pushing out to the CloudFront, we can make CloudFront do the heavy lifting, so that's simply taken off the table. So, in a nutshell, use VPCs. Takes a lot of it off the table, allows you to control the traffic coming in and out. New feature, private DNS, just launched by the Route 53 team. Using that, those servers inside your VPC are only discoverable where you want them to be, so they can't even be found. Take advantage of CloudWatch with its monitoring and alerting so that you know when things are going abnormal. Use ELBs to terminate, distribute the load, and take advantage of auto-scaling. Let CloudFront do the heavy lifting. It's a CDN, that's what they're built for. Diffusing the traffic, spreading it across those 50 locations, so that really scary 400 gigabit attack that we saw. If you divide that down by 52, you get 7 and some change. Suddenly, that's not such a bad number. 400, that's really scary. 7 gigabit attacks, that's manageable. Route 53, make sure you're always discoverable. A lot of the attacks target your DNS infrastructure. Go to the marketplace, see if WAF is the right solution, HA proxy, caching solutions, and plan. Plan in advance. Know how you're going to respond. Know the things that you need to monitor. Know how you're going to engage. We have a resource page on the security website where a lot of this information, plus additional links that you can get a deeper understanding of some of these individual things that I've spoken about, are up there. Engage with your TAM, your account team, for more information. And now, I'm going to hand it over to Adrian, who's going to tell you how this works in reality.
All right. Okay. First, the most important announcement. I know everybody's thinking about party time. I guarantee we'll be done by 6:15. As Andrew mentioned, we've been pleased to be an Amazon Web Services partner for many years. For those of you who aren't familiar with CrownPeak, we are a cloud-based web content management service. So our customers use CrownPeak to manage hundreds, sometimes thousands of websites around the world in more languages than you could possibly imagine. And as you can see, many of our customers are drawn from verticals such as pharmaceuticals, healthcare, financial services, public sector utilities. And so in addition to the concerns they have around regulatory compliance, information security, data protection, they are all very high-profile industry sectors for DDoS-type attacks. So I'm going to tell you a couple of stories. I'm going to tell you one story about how we worked with Amazon to design and then prove to ourselves that we had an infrastructure that we could manage on behalf of our customers that could withstand pretty serious DDoS type attacks. And then I'm going to tell you a story about when we actually happened to have the opportunity to test that in the real world. So before I get into the planning and the testing, big giant disclaimer. Everybody that uses Amazon Web Services signs up to follow the terms and conditions of the services agreement. And the services agreement includes the Amazon Acceptable Use Policy. It's a big, long document, but basically the headline for this talk is you better not mount DDoS attacks, you better not mount vulnerability attacks, otherwise we'll chop you off at the knees. So before attempting to put any of this into practice, if you do even consider doing any kind of specific DDoS testing, I encourage you to reach out to Amazon and explain what you plan to do and secure permission. Otherwise, it'll be the cheapest month after you do that you've ever had with Amazon. So let me tell you a little bit about the configuration that we built for our testing effort. And some very, very common technologies that you see in use around Amazon, and Andrew's mentioned. So first of all, Route 53. One of the things that we do with Route 53, some of our customers choose to host their own DNS. We host DNS for some of our customers. Regardless of who's hosting the domain name that's the public-facing domain name for the website, we always alias that to a Route 53 configuration that's effectively an internal courtesy domain, and we do everything behind that. That enables us to respond very quickly and make changes in real time if we feel we have to, without having to work with a customer and manage a DNS change in potentially a very challenging situation. CloudFront, great. Everybody knows about the value of the CloudFront distribution to distribute static assets, but there are two factors about CloudFront that are particularly relevant to building defenses against DDoS attacks. Number one, it's a massively diffuse service around the world, so any kind of attack is immediately spread around the planet. And for those of you who haven't attended the CloudFront talks at reInvent this week, it also does some very nifty things with pooling TCP connections. So if you have websites that are highly dynamic, that are making calls into JSPs or ASPX pages or other forms of dynamic content, the ability to reuse TCP connections takes a lot of load off the back-end servers, and that's very, very important when you're dealing with a DDoS situation. Elastic load balancing, also a critical part of any DDoS defense. I would point out a couple of things. One is, and it's not actually on this slide, Amazon made a change last year. They introduced something called cross-zone load balancing. Learn it, love it, live it. What it does is, in the days before cross-zone load balancing, Amazon used DNS to hand references to the instances behind the load balancer. And for clients that would cache DNS, that often resulted in uneven patterns of traffic behind the load balancer and uneven loading of the instances. It also made your DNS service a very, very significant vulnerability point during a DDoS attack. Cross-zone load balancing allows the load balancer itself to monitor the health of the instances behind it and ensures that traffic is always perfectly balanced. And if you're adding and removing instances very, very quickly, you really, really want to have it turned on. So for those of you who have had ELBs in production for some time, go back and turn on cross-zone load balancing for all of them. And when you're spinning new ELBs up, make sure you check the box because it's off by default. The other thing that you should also be paying attention to is if you're using ELB health checks to monitor the health of your instances, make sure you're setting a long enough grace period for the instance to actually come up and become alive. Otherwise, you'll find yourself in a situation where your ELB is terminating your instances before they've even come into service. And that's a good way to head into a brick wall really quickly. And the last thing I would say is auto-scaling. If you're building auto-scaling with specific regard for DDoS, I've seen a lot of auto-scaling configurations built using CPU load as a metric. In my opinion, the best evidence of DDoS is an increase in the number of inbound HTTP requests. So the best alarm to set for your scaling group is the network in metric. And I would also encourage you to scale up quickly and decay slowly. In our configurations, we scale up 2 or 4 at a time. But when we scale down, we only scale down 1 at a time because, as Andrew mentioned out, hit and run is very common. And if you've scaled up to defend against an attack, you don't want to destroy all that infrastructure very quickly and then have to scale it all back up again when they come running. So our test plan was built around many, many different types of attack. Some of the slow attacks that Andrew mentioned, where you make a fast request, a slow read. Sometimes you make a slow request. Other attacks where we made a request and disappeared and just left the server waiting to serve a response to a client that no longer was around. We also did a lot of legitimate traffic testing, which actually turned out to be a really good thing, as I'll tell you in a minute. And for those of you who might be familiar with Hulk, I just learned the acronym for Hulk is HTTP Ultimate or Unbelievably Large King. Basically, it's a way of spinning up lots and lots and lots of request threads with an attempt to exhaust the resources of the server very quickly. So these were the types of testings that we did. We set up sometimes hundreds of agents as attack vectors, all of which were multi-threaded. And each of the tests we ran for at least 3 hours because we wanted to make sure that any kind of results we were seeing we could sustain over time, because DDoS attacks are not often short-lived events. And we also made sure that we cooled down because we didn't want any subsequent test to be biased in its results by a successful response to a previous test. And as Andrew was mentioning earlier, we're seeing median attack rates of the order of 0.5 gigabit a second. So we wanted to go for 10x the median. So these were the kind of test parameters we set up. And here are the results that we got in our testing. We were very impressed with ourselves. Here's a graph from CloudWatch. It shows instances scaling up. You can see the steep scale-up gradient and the more shallow decay gradient. This is exactly what we wanted to see: fast scale-up, slow scale-down. And we actually set our scale-up thresholds to have our instances, even though we weren't using CPU load as the CloudWatch alarm, we wanted to make sure we were getting value out of our instances. So we were looking to get an 80%, 90% utilization rate, and we got that. And we had set ourselves the goal of being able to serve around about 1 million requests a minute, and we were able to get that as well. So at this point in the game, we are very impressed with ourselves, and we are ready to handle anything, up to 10 times what the industry says is the norm. So the next part of the presentation, if my wife ever watches this on YouTube, which I don't think is ever going to happen because she's not in the technology business, the subtitle of this section is, "Honey, this is why I never called you from wherever I was that night in April." I travel a lot for my business. I spend all my time working with customers. And one of the things that Andrew mentioned is you really need to be aware of what normal is in your environment and set alarms for when normal isn't happening. So I got off the plane one night in April, and the first thing that I do when I get off a plane is I turn my phone on, and I want to see whether or not there are any CloudWatch alarms going off. And this evening, believe me, something was not right in Toyland. And in the taxi from the airport to the hotel, I was able to take a look and see what was going on, which, by the way, we're all in with Amazon. It's fantastic because it basically means I can monitor and manage my environment wherever I am on the planet. I don't have to be in my office. I don't have to be in my data center. I don't have to be on the end of a VPN connection. Very, very important in this particular scenario. And so what was actually happening was I identified this is a particular CrownPeak customer, also a software as a service provider, very high visibility, and they have a conference in Vegas every year. They have over 15,000 attendees plus supplies. So in actual fact, bigger than reInvent this year. And they were getting unbelievable amounts of traffic on their public-facing web servers on the eve of their national user conference. And they use their national user conference just like Amazon to announce new products, new services. The website is a very integral part of their presentation. And being a software as a service, they have a credibility issue because they need to make sure that they can provide highly available services to their customers. They're in the healthcare industry. I didn't know it then, but what I was witnessing at that time was the beginning of a pretty monumental DDoS attack. It was quite unusual in that all of the requests coming in were 100% legitimate URLs. So we couldn't filter out anything in terms of random traffic. And we were getting attacks from over 100,000 hosts around the world: North Korea, Estonia, Lithuania, China, Russia, South America. But 60% of the traffic was coming from inside the United States. And at the peak of the attack, we were sustaining around about 86 million concurrent connections into our infrastructure. So I'm going to walk you through very quickly the timeline and what actually happened, and some of the changes that we made while the attack was taking place. So 10:30 in the morning Pacific time was when our first CloudWatch alarms went off, and traffic went up dramatically. And what we observed was that the initial log analysis showed that essentially the attacker was dereferencing DNS and attacking IP addresses directly. So we went in behind the scenes, behind our courtesy domain in Route 53, rearranged things, and defended against that attack pretty successfully, cut the traffic out immediately. Those IP addresses were no longer serving any traffic. So at that point, we breathed a sigh of relief in our ignorance and decided that things were going to be okay after all, which they were until 6:24 in the evening. And the attack came back, and it came back with a vengeance, targeting CNAMEs, and the traffic was going up very, very dramatically. I'll show you a chart later on to show you how quickly it ramped up. So we looked at the traffic, and we realized that there were a couple of things that we could do as immediate mitigations. And at the same time, I was on the phone with the CIO of this company, and one of the things you realize about a DDoS attack is very early on, you have a seminal moment. And the seminal moment is, am I going to lay down and die, or am I going to step up? And so he and I made a gentleman's agreement. We agreed that we were going to step up because our reputation was on the line as our service provider to him, his reputation as a service provider to his customers. So we basically agreed that we would split the cost of essentially going to the mat. And our agreement, our handshake agreement, was in the order of tens of thousands of dollars. So we decided that we would go forward and make some changes. I'll tell you what a couple of the changes were. The first thing we did is we realized, because all the traffic was, a lot of the traffic was coming from outside the United States, but this particular customer only served US customers. From some of our work with federal agencies, we had some firewall rules that we knew were battle-tested and would only admit US-based traffic. For those of you who have been with Amazon a long time, HA proxy was the go-to best practice solution before ELB really came to the table. We had also been talking to the FBI, and the FBI was very clear that they wanted as much information as possible to analyze after the attack. So we inserted a WAF sandwich behind our Route 53 configuration and scaled up some HA proxies with these firewall rules, because we knew that would drop 40% of the traffic at the front door, and we also knew that we would be able to get a lot of logging information for the FBI, who had now become my new best friends. The other thing that we also did is we intentionally broke our auto-scaling configuration. Auto-scaling has triggers for when I scale up and another trigger for when I scale down. We changed our scale down trigger to make it much, much, much higher than the scale up trigger. What that meant was we would scale up properly as more traffic came in, but we would never hit the threshold that made us scale down. So our instances would grow and never decay. And the reason we did that is because when autoscale scales down an instance and terminates an instance, the CloudWatch information associated with that instance is lost, and we wanted to preserve that again for the FBI. So we put our game face on, let battle commence. And we had the configuration in place by about 1 in the morning. I'm giving updates every hour to the board of directors at our customer, and the arms race begins. Amazon scales up, our attackers scale up. Amazon scales up some more, our attackers scale up some more. And this continued until around about 7 in the evening on the second day. And at this time, we had around about 17 or 18 C3 8x large HA proxies deployed. We had 30, 35 M3 large web servers because all the traffic was legitimate and all of the US traffic was accessing dynamic pages. It was coming straight through CloudFront and hitting the scaled web server farm behind. But at 7 o'clock in the evening, what happened was really cool because we scaled up and the bad guys didn't scale up anymore. We were sustaining at this point 86 million concurrent connections. We measured the traffic. We were pretty impressed with ourselves that we could deal with 5 gigabits a second, which is 20x or 10x the industry median. But at this point, we were dealing with 20 gigabits a second of sustained traffic through the Amazon infrastructure. So something like 40x the industry median. But the bad guys ran out of gas. So we were serving our customer's website between 1 and 3 seconds. And this continued. They hammered us and hammered us and hammered us, and then at 2 o'clock, they gave up and they went home. Ha. So this is the timeline of the attack. You can see the first attack, the IP-specific one. You can see how quickly the second attack ramped up when they came back. You can see this is a sample of the instances that we scaled up in the web server farm behind the HA proxy sandwich, behind CloudFront, behind Route 53. And then you can see when they gave up and went home. So we got some great feedback from our customer, but Andrew mentioned that I would talk about cost. So I don't want to go too long. I've told you the story. I've told you about the traffic. I've told you about the number of instances we scaled up, how long the attack left. Would anyone care to hazard a guess how much this cost us in direct Amazon service fees? $8,000? Anyone else? $1,500. So was it worth it to go to the mat and scale up and defend our customer against an attack like this? There's no doubt in my mind. And the coolest thing, about 3 hours into the attack on one of the conference calls, one of the senior systems engineers on the customer's IT team who was having a little bit of anxiety, said, you know what, maybe if we can't deal with this in Amazon, maybe we should bring this into our own data center. And the CIO said to him, and he had worked in a very large financial institution before coming to this company, he said, you know what, based on my experience before, if we were in our own data center, we'd have been dead 8 hours ago. So with that, I'll leave you with some encouragement to go and think about this and put this into practice in your own data centers. Thank you very much.